Thanks a lot, Rodrigo, and thanks for having me. And this tutorial is about the causality. Essentially, in this part, you will see some basic concepts related to causality, how we can discover causal information or causal structure or even causal model from observational data or non-experimental data, sometimes known as causal discovery, and how we can infer the causal effect of some variable on some other variable, sometimes known as causal inference or identification of causal effects. And finally, you will also see some connection between causality or causal modeling or causal understanding and machine learning. So you'll see how we can leverage causal understanding to solve some of the machine learning problems. So if you have any questions, please immediately let us know. I would like the tutorial to be more interactive. Okay, now let's start. So here, let's start with some well-known problems in machine learning or artificial intelligence. Right here, you can see an example. In 2015, Google released Google Photos application. It's used for photo categorization. So right here, you can see, oh, this is airplane, it's car, bike, and so on. And unfortunately, you can see right here, this is a huge mistake because African Americans were labeled as gorillas. So this is a big issue. For human beings, right, it's very easy. We can easily do classification in this case. But for machines, it seemed to be very difficult. Actually, after 2.5 years, Google solved the problem. So you can guess how they solved the problem. Give it a try. So essentially, finally, after such a long time, Google just removed the label gorilla from the label set. Now nothing will be classified as a gorilla. You know, gorillas cannot complain. That's why it's a solution, right? But from this example, you can see why, or you can see the difference between machine learning and human learning. Something is very easy, right? This, in particular, this task is very easy for us, but it's very difficult for machines, although we have advanced statistics and machine learning techniques. And right here, you can see another similar example. Here you can see the picture, right? You know it's panda. And then after you add noise in some specific way to the picture, and all of a sudden, the machine will classify this image as something different. And for us, for human beings, clearly it's the same thing. So what happened? Why do we have this issue, right? So essentially, generally speaking, we have this observation. We human beings have our own decision process, right? A way to make decisions. And machines also have a way to make decisions. We have input, right? We process the data and then we give the decision. As long as the two decision processes, one for human being, the other for the machine, are different, then we can have this issue. We can just tune or change the input in some specific way to change the output of one of them, only one of them. So right here, you can see, oh, we just change the input in some way, and then our decision is the same, but the machine's decision is totally different, right? So we have this adversarial attack problem. So how can we solve the problem? Clearly, we have to design the machine's decision process, right? We have to change it so that it's consistent with our process in some way. And what process do we have? We have causal understanding. We have generative modeling. We see the whole world and we want to find a model for the world. And then we make a decision based on our understandings. Right here, right? We extract different features and we make a decision based on the features, those features, interpretable features, but not, machines do not make decisions this way, right? I have raw input, I directly calculate something from the raw input, then I'll give a decision. So you can see the difference. And then what do we mean by artificial intelligence? Right now, I can give some, we can just see some phenomena associated with artificial intelligence. First of all, traditional machine learning usually assumes a fixed distribution of the data. That's why you can train something right here on the training data and then apply the learning machine. you trained, right? Or you obtained from the training data somewhere else. So this is because you believe they have the same distribution. And the classical problem in machine learning is to avoid overfitting, right? However, you can see a lot of problems cannot be understood this way. Right here, if you play, say, tennis very well, then you can easily learn to play other things, and you can easily play them very well. We know how to transfer, we know how to decompose very complicated things into small modules, and we know how to transfer those things to new tasks. And right here to the right, you can see as a human driver, even if the scenario is totally different from what you observed before, you can still understand it. You see the connection between this scenario and the previous ones, and then still you can make right decision, right? But for machines, it's so difficult. Why? Because we know if it's a non-parametric system, then given that they support the test data point, new data point, is not contained in the support of the training data, then basically you don't have a guarantee, right? Anything can happen. Then what do we mean by intelligence? So first of all, we know if we are intelligent, then we are able to understand what's going on. We have the ability to understand the environment. Of course, here I don't give a definition of understanding, but basically, we know if something is intelligent, then intelligence should have the ability to understand what's going on. Later, we will have a better definition of understanding. And because of the understanding, we can do control or intervention in some specific way to achieve our goal. We can decompose very complex things into simpler, small things, right? Modules. And then we can just combine different modules, small modules, to build a big thing, to have a big picture, known as information fusion. And we can do learning with few examples by making use of our experience, right? And we can do not only interpolation, but also extrapolation, right? We can go beyond the experience because we can understand the relationship. We know, oh, even if the distribution is different, we know something can still apply, right? So for machines, this is very difficult. And we just saw what intelligence or what artificial intelligence could do. How can we really achieve artificial intelligence, right? Well, some people may say, oh yeah, we can just study how the brain works, and then we can just construct something to completely mimic that. Then this is the typical machine learning way to achieve artificial intelligence, right? Given a particular data set, you want to construct something optimal for that data set, but it's not general. So let's try to have a general understanding of intelligence. Let's use the evolution, selection, and growth perspective. So we define intelligence because we survive, we prosper, then we think we are intelligent, then we want to find something to characterize this particular property, right? So first of all, we survive, right? And we prosper. That means we have the good, we can make good prediction and decision across different scenarios, across all scenarios. And statistically speaking, to do this, we have to form some inner compact representation of the external world. This way we have a simple model, right, for everything, and we know how different things are related, then we can make good prediction. We can leverage information from other places, right? And furthermore, we are creative. We can change the world. We can just build new things, right? So creativity relies on causal representations of the world. Right here, we have the two abilities, and they are related. They are somehow consistent. When we were very young, right, we couldn't really do interventions. And by observing and thinking, we could form some kind of representations. And later, we can do manipulations. We can verify a lot of things. And there does not seem to be a huge gap between the two types of representations. So now, the first thing is about prediction, and the second thing is about causality. Because they are somehow consistent, and now we can try to solve the following problems. First, how can I analyze data without doing manipulation to find the causal information? This is the causal discovery. Second, Suppose I have a causal representation or causal understanding. How can I make use of such information or such knowledge to make good prediction across scenarios? This is something like transfer learning, right? So essentially, in this tutorial, you will see how we can do causal discovery and how we can leverage causal information to solve other problems. Questions? If you have any questions, please immediately let us know. Okay, so we know that we have to distinguish between causality and association. In data, we can easily discover association, right? But causality is clearly more important in most situations. Here you can see some examples, but this is the news report from the Telegraph. And it says couples who share the housework are more likely to divorce. Okay, this sounds horrible, right? So that's why it's not surprising that people had a lot of follow-up discussions. For instance, here, right here you can see, does sharing housework really lead to divorce? So for us, we want to get some information as to what we can do to make things better, right? That means we really want to find the causal understanding of the phenomenon. Right here, we use the word lead to, so this is the causal. We want to find the cause. We want to see whether this relationship is causal or not. And without the causal understanding, we cannot really change the environment properly. Okay, so what's causality? What's the dependence? We know that it's very famous. This statement is very famous. It says causation implies correlation, but the correlation doesn't imply causation, right? So here, basically, we can say, yeah, that's true. However, maybe it's better or it's more fair to say that causation implies correlation, but the correlation doesn't directly imply causation. Under some assumptions, or if you have additional information, then immediately you can find the causation from correlation or dependence. When I was very young, I used to think that correlation implies causation, right? It's not surprising. And then after taking some statistics classes, I changed my mind. Most people did that. And then after doing research in the field for some time, now I'm very optimistic. Basically, we can say that in almost all situations, with rather weak assumptions, we can really discover causal information from various kinds of observational data. Sometimes we have IID data, sometimes we have time series, sometimes we have non-stationary data, and so on. But in all cases, we can discover causal information under the suitable assumptions. So we say two variables are associated if and only if they are dependent. As you can see from here, on the left, you can see the definition of dependence. Now, we say they're dependent if and only if different values of one variable correspond to different distributions of the other variable. Meaning that if I want to model or predict the other variable, say y, then x would be useful, right? And when we say x is the cause of y, we mean the following thing. We have a particular way to change the system. In particular, we want to change x, only x. Then after you change x, if you observe a change in the distribution y, then we say x causes y. And here by change, I actually mean intervention, intervene on this variable. So what does it mean by intervention? Essentially, when you want to intervene on x, you have to guarantee that, at least for the moment, no other variable is changed by this intervention. You only change x. And then if you guarantee that, I only change x, now I observe the change in y, then there must be a way for x to change y. In other words, x is the cause of y. Okay, so of course, this definition of causality is a kind of circular, right? Because if you have no idea about the causality, how can you make sure this is the right intervention? How can you be sure that, no other variable is changed by this particular action, right? But circular definition can still be very useful. So how can we find the causality? A traditional way to find the causality is to do manipulation or intervention. So, here you can consider some examples. Or you can think of causality from this perspective, or you can verify whether variables are causally related by imagine how intervention or the effect of interventions. So right here in the first example, we have very hot weather, right? And we have high sales of ice cream. So in this case, if there are causal relationship between the two events or variables, you can consider them as binary random variables. So you can see, oh, yes, I can do intervention. So here I can, if I can find a way to make it very hot, right? Then a lot of people will buy ice cream. It's very natural. However, I can find a way to increase the sales of ice cream. Say, I can just hire a lot of people to buy ice cream. This is the intervention because this action will not directly change the other variable. But then you can see, oh, this action or the high sales of ice cream will not make the weather hot. That's why we can see, oh, the first event causes the second one, but not the other way around. And then let's look at a second example right here on the right. Here we have one event, which is a bus coming. And right here, the second event said that the guy is leaving home. Suppose this guy go to work by bus every day, every work day. So around 8:30, this guy is leaving home and the bus is coming. So the two things are clearly correlated, related, right? They are dependent. Now, do you think there is a direct causal relationship between the two events? They are related, right? So you can think of, just think of the causal relationship. Now, intuitively, yeah, there might be a causal relationship between them. Then it's very surprising because there are no physical way for them to be related, right? How can I have a causal relationship between them? Then let's look at a problem from the intervention perspective. So suppose the bus is coming. Now I want to do intervention. For instance, I can just jump in front of the bus. Hopefully the bus will, that's very bad, but the bus will stop, right? This action will not change this guy's behavior directly. Now you can see the bus stops and that guy will still leave home as usual. That means the bus coming is not a cause of the guy leaving home. And similarly, suppose the guy is about to leave home. I just suddenly close the door, right? The guy will stay home and you can see the bus will still come as usual. Now you can see there are no direct causal relationship between the two events, but they are dependent. Why? It's because we have some common cause, right? In most cities, we have timetable, and timetable is a common cause of two different events. And of course, you can say, oh, now I want to change the second event right here. Maybe I can just change the timetable, right? That's a change. However, that's not an intervention because if you change timetable, then the other variable or the other event will also be changed by the action. That's why it's not an intervention. So in order to verify that it's really causal, you have to guarantee that your action is an intervention. Otherwise, things can be very complicated. However, now you can see, given that it's really hard to apply interventions, how can we really discover causal information in reality? So we have to make use of a lot of information. Sometimes we have temporal information because in most cases, causes happen before effects. And we have, we have understanding of some very simple causal mechanisms, and then we can combine the causal mechanism to understand complex systems to have causal information, right? And sometimes we can really discover causal information by observing and analyzing the data. So typically, there are three types of problems in artificial intelligence. Right here, let's just have a quick look at the problems. The first one is known as prediction. So here I have data. I have three variables, x1, 2, 3. I have data. Now I want to see, answer the following question. Would the person cough if we find he or she had yellow fingers? So here x1 denotes smoking, x2 yellow fingers, and x3 whether the person coughs. Okay. So now you can see this is just a prediction problem. And this relies on this conditional distribution of x3 given x2. You can use linear regression, logistic regression, deep networks to derive essential features of this conditional distribution to make a prediction. Right here, only the observed data, right, are needed. You can just directly find something of this conditional distribution. The second type of questions is about intervention. So you want to see the effects of interventions. And clearly, this is the causal problem. And sometimes intervention is also known as manipulation. So typical questions are like this one. Would the person cough if we make sure that he or she has yellow fingers? So we do intervention, right? We just make sure the finger color is yellow. And then we want to see whether a person cough. Now you can see the probability distribution of x3 given intervention x2. And this is known as interventional distribution. And to do so, clearly we have to make use of causal picture. And the third one is more detailed, is known as counterfactual reasoning or counterfactual inference. So the question is as follows. Would George, a particular person, cough had he had yellow fingers, given that he does not have yellow fingers and coughs? Now you can see compared to the second question, we have this condition. We observe something. Right here, we observe that George does not have yellow fingers and coughs. So we can just write down this, formulate this problem this way. We want to say something about x3 after we do intervention x2. Right here, this is intervention, given this condition we observe. And this is counterfactual because we already see something about George. George does not have yellow fingers and George coughs. Now we want to do something that is not realistic, right? We know this is going on, and we want to see what if something had been different. What if George had actually had yellow fingers? So this is known as the counterfactual because you are doing something like reflection. You want to reflect something that already happened, and then suppose you can change something. You want to see the effect of that change, that relative to this particular unit you are talking about. So here in this example, we are talking about George, a particular person. Okay. So this is the outline of this tutorial. So essentially, we have 4 parts. First, we'll see what we can benefit from causal thinking. And I will give a brief introduction to graphical models because we use a graph to represent the causal relations. And then in the second part, we'll see how we can learn causality. In particular, we will see how we can make use of the so-called constraint-based methods for causal discovery. And we'll also see how we can consider practical issues by developing extensions of classical methods, constraint-based methods for causal discovery. Here, by constraint, I mean conditional independence constraint. Later, you'll see why we use this name. And then the next part, we'll see how linear non-Gaussian method or nonlinear method can be derived for causal discovery. So here we make use of additional assumptions of the causal mechanism, and then as a consequence, we can learn more information about the causal structure. And also we'll see how we can extend those methods to deal with practical issues. And then we'll have a very quick look at how to identify causal effects of some variable on some other variable. And finally, we'll see how we can leverage causality in solving machine learning problems, including domain adaptation and image-to-image translation. Causal thinking. So here I will give 3 examples to illustrate what we can benefit from causal thinking. First, this example was used by Fisher in the 1950s. Here, smoking is a common cause of yellow fingers and lung cancer or lung disease. And now you can see it's not surprising that yellow fingers and lung cancer are dependent. However, if you want to change the incidence of lung cancer in a particular area, what can we do? We cannot just change the color of the fingers, right? We have to go to the cause. We have to change smoking variable. So now you can see, if you want to change something, you have to care about the causality. If you just want to make passive prediction, yes, dependence will be enough. In a classical IID setting that you will see in some other scenarios, to make a prediction in complex situations, sometimes we still need the causal information. Okay, this is about the difference between dependence and causality. And the second example is about confounding. The third example is about the selection. This is the second example. So this was a real data set here. So it's about the patients with kidney stones. So we have two groups of patients. One of them has small stones and the other has large stones, this row and that row. And we have two treatments, A and B. Now you can see, as you can see from the table, no matter which group you are considering, treatment A is better, right? Right here for small stones, the recovery rate, this number is the recovery rate, is 93% versus 87%. So A is better. And for the group with large stones, the same thing happens because treatment A has a recovery rate 73%, which is higher than 69%, right? And now, if you combine the data, just consider the whole data set, and you can see, oh, treatment A has a recovery rate 78%, and B has 83%. B is better. So now comes the question. Suppose now you are a doctor, and suppose you only care about the recovery rate, means that you just want to maximize the chance of recovery. And now, suppose a new patient just come to you. Would you recommend A or B? Right? You may say A, yeah, if I know the stone is small, I will recommend A. If I know the stone is large, I will recommend A. If I don't know that, I will recommend B. That's why we say it's a paradox. Clearly, the stone is either small or large. You will recommend either A or A, and finally recommend B. That's the problem, right? So why do we have this issue? This is because the stone size is actually a common cause for treatment and recovery. And when we do when you make recommendations, you only care about this link, called the link from treatment to recovery. You don't care about the stone size. You care about this effect. However, because of the existence of stone size as a common cause for treatment and recovery, the dependence pattern in particular, the correlation between treatment and recovery can be rather arbitrary. This correlation does not reflect the information of the causal influence, does not really reflect the causal effect at all because of this common cause. That's the problem. So right here you can see another example from Pearl's book. So here X and Y are the X size and the collateral respectively. And you can see right here we have different age groups, 10, 20, 30, and so on. So you can see for each age group, the more exercise you do, the less collateral you are going to have on average. That's very good. That means, we should do more exercise to reduce collateral. However, if you ignore the age information, now you can see collateral and exercise are positively correlated. Seems that, the more exercise you do, the more collateral you are going to have. That's horrible. And we have this phenomenon because we just ignore the common cause, which is the age right here. And when you do recommendation, you only care about the causal effect, not correlation. Okay. Now let's consider third example. So let's go back 50 years. Now you would find that female college students are smarter than male students on average. Why? We believe that overall, females and males are kind of equally smart, right? In some way. So why do we have this phenomenon? Someone is speaking? No?
No.
Okay, thank you. So why do we have this phenomenon? Basically, this is a selection problem. At that time, it's rather difficult for females to be admitted to college. Right here, you can see gender and IQ are both causes of being admitted. And although they were originally independent, gender and IQ were originally independent, given the common effect, usually they are not independent anymore. They are dependent. So to give a very concrete example, just think of college as the sum of gender and IQ. If I know the sum, then the two variables will not be correlated, will not be independent, right? The larger this guy, the smaller this guy on average, because I know the sum. So this is a particular type of dependence introduced by selection problem, selection phenomenon. Okay, here you can see another example. Here, right here, you can see a lot of holes in the airplanes that return from wars, right? Now let's try to answer the following question. Suppose you want to make the airplane better by putting some armors somewhere on the airplane. So would you like to put the armors here or here? Right? Some people may say, oh, here you can see a lot of holes. That's why we should put armor there to make this part stronger. So here, clearly, we have to make use of the process. This is the process being hit, the airplane. One variable, the other variable is where it got hit. And then both of them are causes of survival, right? So airplanes came back, that's why they survived. And then we observe the probability distribution of B and W in hit and where given the airplane survived, right? We just see the holes in the airplanes that came back from wars. And then, to put the armor in the right place, we want to infer the following thing. We want to infer the distribution of B and W where, given that S is zero, meaning that we just care about the airplanes that failed to come back. And then we want to change it. We would like those airplanes to come back. What can we do? We have to consider where the holes are, right? For those airplanes. And then we have to put the armor there, right? Here, 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 and so on. So now if you have this causal picture and observe the data points, you can just answer this question very easily and rigorously. Okay, to summarize, if you want to do active manipulation or intervention to achieve your goal in the system, then we care about the causality. And if you just do passive prediction, giving a particular distribution or giving data points drawing from a particular distribution, then you only care about the association of information or the distribution. And if you want to do a generalization or adaptation, then in most cases, you care about the causality. So tomorrow you are going to see some examples. And if you want to do knowledge integration, most of the time, we really have to make use of causal representations. Here, you can see some examples. Suppose X causes Y, and that Y causes Z, right? Now you see, oh, no matter what, X causes Y and causes Z, right? X causes Y, and then further causes Z. You have a big picture. You have understanding over X, Y, Z together. However, if you know that X, Y are dependent, and that Y, Z are dependent, now what's the relationship between X and Z? You have no idea, right? X and Z can be identical, can be independent, and so on. So if you just make use of association information, you cannot go further. You cannot derive a big picture. But if you really have a causal understanding of the system, you can just have a much better understanding. And that's why we can build aircrafts, right? We know different modules, and then we put different modules together in the right way, then we have the bigger system. And because of causality, we are creative. Let's say we have creativity. So what's the creativity? Essentially, we want to answer the following question. What if something had been different, right? I observe this, and then I want to make a difference. How can I make a difference? I have to imagine something. If something had happened, what would happen, right? This is the difference. And so this is a counterfactual question. And furthermore, you have to answer such question. You have to do knowledge integration and so on. So basically, those things are related to causality. Okay, now let me give a quick introduction to graphical models. Probably we should just pause for 1 minute for questions. If you have questions, please just write. You can raise your hand, or you can just write the questions in the chat window. No? Okay, then let's continue. So right here, you can see a graphical representation of the relationships between a lot of variables. So right here, you have anxiety, peer pressure, smoking, and so on. So with this graphical representation, you can see we have a very nice understanding of the relationships. We know, oh, anxiety influences smoking, and then further influences lung cancer, and so on. This is very intuitive. So this is what we can benefit from graphical representations. Here, a graph has nodes, and we have links to connect the variables or the nodes. And this is the graphical representation. And we use a probabilistic graphical model to encode a complex distribution in a very intuitive and compact way. So right here, each node is a random variable because we are talking about a probabilistic graphical models. We want to model distribution. So each node is a random variable, and each link represents a direct probabilistic interaction between them. Now we are not talking about causality. The link right here, the link is not necessarily causal, but later we have to further attach some constraint to the graphical representation, and then we can make sure that the graphical representations are causal. So essentially now we just combine two things. One, the graph theory, which provides a very intuitive way to see the relationships, and probabilistic theory, which can be used to represent uncertainty in the variables or the relationships. And if you combine them, we have a very nice way to have an intuitive way to represent the distributions. Okay. So we are particularly interested in directed graphical models. And in most cases, we are concerned with a directed acyclic graph in which we don't have any loop. So if you go from one variable, you will not go back. And these kind of graphs are also known as the Bayesian networks or belief nets. Right here, you can see an example. And right here, directed graphical representation graphs or Bayesian networks have two components. One is about the structure, qualitative specification of the relationships. And the other is a quantitative part. We have to attach either conditional distributions or some models to represent the probabilities of some variables given other variables. So finally, we can have the joint distribution of all the variables. So for the graphical structure, in many cases, we can just build a structure. We can just have the structure based on our understanding of the problem, and sometimes we can learn it from data. And the quantitative part can sometimes be a conditional distribution, and it can also be some equations, some structure equation models. I will give the definition of a structure equation model later. So in graphical model, we have a lot of terms. Here, right here, you have a node. This is the node. This is the edge. And if there's the edge between them, we say they are adjacent. And right here, we have a path. And in particular, this is a directed path because we just follow the same direction, right? Go from cloudy to sprinkler to red grass. This is a directed path. And this is a path, but it's not directed. And right here, sprinkler and rain are parents of wet grass. They are adjacent, they are causes, they are ancestors. Later we define ancestor. And this is the children. In particular here, sprinkler and rain are the children of cloudy. And sprinkler and rain are spouses because they have a child, which is wet grass. And all the other variables are the ancestors of wet grass. They are either they are either parents or parents and parents or parents, and so on. And all the other variables are descendants of Causality because they are either children or children's children, and so on. And later we'll have the definition of Markov blanket. Okay. So typically, there are three types of questions related to Bayesian networks. The first one is called probabilistic inference. So right here, we are given this structure, and we are given conditional distributions. And then suppose we know the value of some variable, then we want to infer the probability of some other variable, right? Right here, you want to find the posterior of some variable given the some of the observed value for some other variable. And this is called probabilistic inference. The second one is the parameter learning. So right here, given data, how can I learn, say, parameters in the conditional distribution or parameters in the structured K models and so on. And the last one is known as structured learning. So you want to learn the structure of the graphical model from observed data from a data set. And right here, this structured learning is not necessarily causal learning, not necessarily causal discovery, because this structure is not necessarily causal. For instance, if you have two variables, in many cases, you just want to determine whether two variables are adjacent if you want to learn a Bayesian network. But from the causal perspective, we have to carefully distinguish between different directions, right? Okay, so now suppose you are given this directed graphical representation right here. What independence relationship can you infer or can you see regarding the variables? And right here, to do so, we can apply the so-called local Markov condition. Each variable is independent or conditionally independent from its non-descendants given its parents, meaning that right here, yellow finger will be independent from cancer given smoking because cancer is the non-descendant of yellow finger. And in this example, falling down will be independent from rain given slippery ground, right? This is the local Markov condition. It's nice because once we have the graphical representation, we can immediately see whether the variables are conditionally independent. However, it's not enough because we want to see whether two arbitrary sets of variables are conditionally independent given some other variables. So in this case, we cannot directly apply local Markov condition. We have to use something different, which is a deseparation. So basically, if you know deseparation relationships, then we have the following thing. If every path from a node in X set of variables to a node in Y, another set of variables, is deseparated by Z, then X and Y are conditionally independent given Z. This is known as the global Markov condition. And here by D, I mean directional. Let you see why, because we care about the direction of the path. Now, definition of deseparation. So we have three sets of variables, X and Y and Z. So we say Z deseparates X and Y if every path from any node in X to any node in Y is blocked given Z. Okay, so every path between X and Y is blocked by Z. Now comes the definition of blocked, right? What do I mean by blocked? So right here, we say a path is blocked by a set of variables Z or set of nodes Z if at least one of the following conditions holds true. If one of them holds true, then we say it's blocked. Of course, if both of them hold true, clearly it's blocked. The first condition said that this path contains a chain I to M to J or a common cause right here. M is a common cause such that the middle node M is in Z. So if M is in Z, then you can see right here, if I know M, or if I condition on M, I just cut this off, right? And the second condition said that P contains a collider or common effect, M right here, such that the middle node M is not in Z, the condition set, and no descendant of M is in Z. Now, let's try to understand this condition or those conditions in light of examples. So right here, we have a directed graph over x, r, s, t, u, v, y. So do you think x and y are deseparated by r and v? X and y are deseparated by r and v? Yes or no? So clearly it's yes, because the first we only have a single path between x and y, and the first condition holds. V right here is a common cause, it's in Z. Second question, do you think S and U right here, S and U are deseparated by R and V? So S right here, U right here. Do you think S and U are deseparated by R and V? Yes or no? Answer is also yes, because the second condition holds true. We have a collider or common effect here, and we know T is not in the condition set, and no descendant of T is in the condition set. Okay, right here you have you can see more examples. Basically, this is known as a global Markov condition. If x and y are deseparated by Z, then x and y are conditionally independent given Z, or conditioned on Z. Okay, let's give the examples. Okay, so now we have two Markov conditions, local Markov condition and a global Markov condition. If you are dealing with the DAGs, then the two conditions are equivalent. So you can prove a global Markov condition by making use of a local Markov condition and vice versa. It's nice because now we can easily see conditional independent relations from graphs. And now comes the definition of Markov blanket. So if you are given a DAG, then the Markov blanket of any node is a set of variables consisting of parents of x, children of x, and the parents of children of x, basically other parents of children of x. So for instance, suppose let's consider I here. Then the Markov blanket of I would be the set of variables E, K, L, H, J, right? Parents, children, other parents of children. And then we have this very nice property. All the remaining variables will be conditionally independent from this variable I, given the Markov blanket. And you can easily prove that. Why? Because all the other variables will be deseparated from this variable I, given the Markov blanket of I. Okay, you can see all paths are blocked by the Markov blanket. Okay, this is the Markov blanket. And we can learn DAGs, or we can learn graphical representation from data, right? There are many methods to learn Bayesian networks. So sometimes they are causal, but sometimes they are not. Causality is not just about the conditional independence. In particular, in the two variable case, right? No matter how, no matter which way the direction goes, we say they can represent the same distribution, right? However, from a causal perspective, they are totally different. X causes Y, right? And this case totally different from the situation where Y causes X. How can we be sure that the DAG representation is causal? Right here, you can see we have a graphical representation. In order to be sure that this is causal, we have to attach some conditions. And clearly, based on the definition of causality, based on intervention, we know we have to introduce the intervention right here. So there are basically three conditions. Here by PXV, I mean the distribution of V resulting from intervention on X. So this is PXV. And then first condition said that this interventional distribution is Markov relative to G. So we still have conditional independent relations seen from the graphical representation. The second one is also pretty trivial. It says if you do intervention, then the probability for instance here, if you do intervention to set the value of x3 to on, then the probability for x3 to be on is 1. That's for sure, right? You just set the value to some constant, then the probability will be 1. The last one is very important. It says that the interventional distribution, conditional distribution, is the same as the original distribution if I do not intervene on this variable v. So if I do not intervene on this variable, then the conditional distribution of this variable on its parents would be the same across the two graphical representations. Right here, we have, this is the effect of intervention, right? This is the post-intervention distribution. And this is the before intervention distribution. Essentially, the two models will give you the same conditional distribution. In other words, even if you do interventions, you can see I can still use the conditional distribution I have before. In other words, this intervention is local, or we can say this representation is modular. We have separate modules for the causal system. If I do intervention here, then this conditional distribution and this conditional distribution will not be changed by that. This is known as modularity. Okay, this is one way to represent the causal relations. You use the causal directed sacral graph. So alternatively, we can use the so-called structural equation models or structural causal models. So now we don't use the graph. However, we can use a set of equations. We know x1 causes x3. This is x2. x1 causes x2. Then x2 can be written as a function of x1 and some other omitted factors or noise. And x3 can also be written as a function of x1 and some other omitted factors, e3, and so on. So right here, from this set of equations, you see the causal relations. You know, x1 is the direct cause of x2, x1 direct cause of x3, 2 and 3 are direct causes of 4, and so on. And that's why we say this is a structural equation model, because this provides a mechanism to assign the values to the variables on the left-hand side of the equation by making use of the values of the variables on the right-hand side of the equation. So we use the value of x1 to determine x2, although it's probabilistic, right? We have noise right here. So this is called the structural equation model. And we say each equation represents an autonomous mechanism because we can just change one of them without changing any other variable, also known as modularity. And so basically, we have two ways to represent the causal relations. And then the next part, you'll see how we can learn causality, causal relations from observational data. Okay. So this is for the first part. If you have questions, maybe you can ask them. Otherwise, let's just come back in 6 or 7 minutes. Thank you.
All right. Then let's have a short break. No problem.
Should I just stop sharing the screen?
Yes, you can. So you can turn down the.
Yeah, I'll come back. Yeah, I'll come back in 4 minutes. Is that good?
Yes, no problem. So and you can mute and also turn off the camera and screen sharing. So it's no problem.
Wonderful.
Yes, so we can start with the questions and then we can continue with the regular.
Okay, great. So I just saw the questions in the chat window. It's really nice. The first one, sorry, it's not easy for, for me to pronounce the name. The first one, nice, is the answer to the question is B, because there were more males, yeah, put where there are no holes. That's very good. Yeah, exactly. And there is a selection bias. Yes, survival paradox. Yeah, and this is not a question. This is not a question. Okay, question. Maybe one general question. Without the intervention, we cannot learn about the causal relationships. Is that right? I would say no. Even without interventions, as you can see, as you will see in 5 or 10 minutes, we can really discover causal information. And furthermore, in some cases, even if we have confounders, which are the unmeasured direct common causes of two variables in the system, we can still discover causal information under very mild assumptions. So basically, the answer is we can. And then mathematically, is the probability distribution of x given do y in this notation. What does do y mean? Okay, that's a very good one. I didn't mention that. Let me just go back. First, hereby do. Let me give the slide. Go to the slide where I first gave this notation. Right here. So here, see, do just means intervention. Do x equal to x1 means that I do intervention on x to set the value of x, variable x, to x1. This is intervention. And now you can see, not surprisingly, you can see the connection between intervention and this graphical representation of the post-intervention distribution right here. Compare the second graph with the first one, you can see we do intervention on sprinkler to set sprinkler, this variable, to on. We set the value right to on. Now, since we are doing intervention right here, all the causal influences into this variable will disappear because we just use a new way to set the value of x3, right? It's not influenced by those variable original causes anymore. That's why when graphically speaking, when we do intervention represented by do x equal to x1, we just do the following thing. Graphically speaking, we cut off all those edges into this variable and we directly set the value of this variable to some specific one, say x1. Okay, that's the difference between this representation, original representation, and this representation for the intervention in post-intervention distribution of the variables. Okay, and then I have a question about the chain example x, y to z. Is there a case that we also have a connection from x to z as well? That's wonderful. Yes, it's possible, right? So when you try to integrate information from different aspects, yeah, you may be able to make the information more specific or precise because it's not, in many cases, we do not have a unique solution, right? We know, yeah, x, in any case, x is the cause of z, but we don't know whether x is also a direct cause of z, right? In any case, we have information. And furthermore, you just raise a very nice question. In some cases, we have to go further to see whether the solution is unique and how we can do this procedure more efficiently and so on. Very good. The answer is yes. Okay. There are no other questions, so let's just continue the lecture. Okay. So now let's try to learn causality as the answer to the previous question. Very good question. So what can we do? Here, for human beings, right, we can learn causality. And in many cases, we make use of temporal information, temporal order information. we know cause is happening before effects. Right here, you can see a problem. Actually, this is a problem in my 4-year-old son's homework. So you can see kids can really determine the order very easily. And also at the same time, you can say, yeah, if this happens before that, then this is the cause of that in some way, right? First of all, yeah, this is reasonable. Second of all, this is not necessarily the case. In many cases, we cannot discover causal information from temporal information. And third of all, in many cases, we do not have temporal information, right? We may have ID data, or we may have very low resolution of the data. Suppose the causality happens very fast, and suppose you have very low resolution data. What can you do? You cannot just rely on the temporal information. That means we really have to go further to discover, to find the characterizations of causal information in the data, or to find the kind of footprint of causal influence in the data. Actually, we can. And this is very general because once you solve the problem without making use of temporal information, right? Then if you are giving causal temporal information, that's just additional constraint you can make use of. That's why let's just start with a very general problem without temporal information. So here you can see an example. Actually, this is a very nice paper published in Science a couple of years ago. So as you can see from the title, it's a causal problem, say large-scale psychological differences within China can be explained by rice versus wheat agriculture. Means that agriculture causes culture or psychological difference. So clearly, here we don't have temporal information. We don't have the temporal precedence information, right? And we cannot do intervention. You cannot force people to change their agriculture, right? Even if you can do so, you have to wait a very long time to see the effects. That's why, in that case, we cannot really do intervention and make use of interventional data. We have to discover causal information by analyzing the observed data. And actually, the conclusion of this paper is rather strong. It says, yeah, they said a history of farming rice makes cultures more interdependent, whereas farming wheat makes cultures more independent. So you can see this is a causal explanation. Also, they try to control for possible confounders like climate and so on. So it's very nice. Right here, mathematically, you can see we have variables x, y, z. They can be a set of confounders, and they just discover the set of independence and dependence relationships, conditional dependent relationships. And then under some very mild assumptions, they can say x causes y. That's very nice. That's how you can discover causal information by analyzing data. You will see the procedure. This is another example. Right here is my collaborator, Marlene Nobeck. Her last name is very cool, Nobeck. Just go forward, look forward. So she collected she collected 250 skeletons all over the world. And she measured 8 variables, including gender or sex, cranial size, diet, and cranial shape differentiation. So essentially how it looks. Essentially, in archaeology, they really want to see how and why people from different areas look different. And also based on the understanding, they want to make prediction into the future. So that's very nice. Clearly, you cannot do intervention. You cannot wait to see the effects of interventions, right? You have to analyze those collected data skeletons. Later, you see the results. So, okay, now let me give some basic concepts. The first one is the causal sufficiency. Here we have a set of variables, V. We say V is causally sufficient if V contains every direct cause of 2 variables in the system in V. Right here, you can see we have Z, X, Y, and Z is a common cause, direct common cause of X and Y. And if V is Z, X, Y together, we say it's causally sufficient. And if V is just X and Y without Z, we say it's not causally sufficient or causally insufficient. Why? This is because the direct common cause of X and Y, 2 variables, which is Z, right? is not in the system in V, the set of variables. That's why we say this set of variables is causally insufficient. Most methods for causal discovery assume causal sufficiency. So basically that means there are no missing or there are no unmeasured direct common cause of two variables in the system. And also we define confounder this way. Confounder is the unmeasured direct cause of two variables in the system. So if right here V is just X and Y, we say Z is a confounder. However, some methods can handle confounders. For instance, the FCI, fast causal inference method, can still give the right solution, results, even if there are confounders in the system. And later you'll see some examples. Okay, this is the causal sufficiency. And the second thing I want to emphasize is called V structure. Right here, you can see we have three variables: cold winter, snow, slippery ground. We have this particular structure, right? The two causes are going to this variable. This is called a V structure. And sometimes this is also called unshielded collider, because we have this common effect and they are not shielded. So this is particularly interesting. Why? This is because among the four causal structures with the same adjacency, you can see right here, this one is totally different from the rest, the remaining three. Right here, we can see, oh, this is the first case, this is second, third, and fourth, right? In the first case, according to Markov condition, local global Markov condition, we know cold winter is independent from snow, and they are conditionally dependent given slippery ground. Right here, you can see that because of this separation, right? Or we can say they are independent, originally independent, right? Given this variable, we don't know, but we know that they are not conditionally independent according to the causal Markov condition. However, in the remaining cases, all those three cases, we see the same set of independence relations. We see, oh, cold winter will be conditionally independent from snow given slippery ground, right? So in all those three cases, we see the same set of conditionally independent relations. Okay, let me just have a look at the chat window because I saw some message. Oh, not a question, thank you. Okay, so here, now you can see, oh, if I know the skeleton, right here, by skeleton, I mean the adjacencies without directions, then I can distinguish between this particular case and the remaining cases by making use of conditional independence between the variables. Okay, this is very important. Now, let's try to do causal discovery. The definition of causal discovery is as follows. We are given observational data, and you want to recover the causal structure or some essential information of the causal structure by analyzing the observational or non-experimental data. So now what can we do? We want to go from data to the graph, right? So how can we connect the two things at different levels, right? First of all, we have Markov condition. For instance, if you apply global Markov condition, we have the following thing. If two variables are deseparated by another variable z in the graph, then we know they are conditionally independent, right? So we can go from graph to independent relations. How can we go back? First of all, if you want to go back, you have to apply something like counterpolative of this proposition. That means if you see conditional dependence between x and y given z, then x and y are not deseparated or deconnected by z, right? So this is the counterpolative of the proposition. What if the variables are conditionally independent? You have no idea, right? We only know that, oh, if they are conditionally dependent, then they are deconnected. If they are independent, we have no idea, according to this global Markov condition. And if this is the case, for any data, we can always give a graph to satisfy the Markov condition. What graph? We can always use a fully connected graph, right? Each pair of the variables is adjacent. Then you can see global Markov condition, this guy is always true. Because this guy says, oh, if they are deseparated by Z, they are conditionally independent given Z. In this graph, fully connected graph, no pair of variables is deseparated by any other variable. As a consequence, you can say, oh, I cannot see conditional independent relations in the data. If you really see that, it could be something you observe by accident, right? It's not necessarily the consequence of this condition, meaning that this condition still holds true, right? Because if the condition is violated, then we cannot say anything about the conclusion. So this solution is trivial because you always provide a fully connected graph. How can we find a simple informative graph from data? That means we have to make use of conditional independent relations in the data. In other words, how can we go from conditional independent to deseparation, right? Go from the right-hand side to the left-hand side. Now we need two things. One is the Markov condition, you know that. If you know the graph, then each variable is a conditional independent from its non-descendant, or we can say if two variables are deseparated by the third one, then they are conditionally independent given the third one. This is a Markov condition. In addition, we have another condition called faithfulness. So faithfulness says that all observed independence or conditional independent relations in the variables are actually entailed by Markov condition on the causal graph. It means that if I observe the independence between y and z given x, then this is the property of the graph. If you apply Markov condition and observe this conditional independence, you know that, oh, y and z must be deseparated by x. In other words, now we can go from conditional independent relationship to deseparation. Okay. So this is the faithfulness condition. And the faithfulness condition is very interesting. You can just think of faithfulness condition as something like a faithfulness relationship between a couple, right? That there's some kind of one-to-one mapping between different things. Okay. So again, faithfulness assumption says that all observed independent relationships are actually properties of the graph according to the Markov condition. In other words, there's no accidental independence relationship in the data compared to the graph or compared to the set of relationships implied by the Markov condition on the graph. Okay, think about it. Make sure everything is natural to you. Now, let me just say a few words about the faithfulness assumption. In this example, with the three variables, health condition, healthy lifestyle, and then mortality risk. Let me have a look at the chat window. Okay, let's just pause here. We have a question from Shreya. What is the intuition behind the concept of deseparation and behind the deseparation conditions? Okay, so deseparation is just a property of the graph, right? So essentially, by deseparation, intuition is as follows: if x and y deseparated by z, then they are given. If you know z, if you condition on z, then there is no other way for x and y, no way for x and y to be related in the graph. This is intuition. Let me just go back. So here, this is the picture to give some kind of intuition. We have variables A, B, C, D, E, F, G, right? And here we can just use the basically here. We can just use the tabs. And giving something means that this guy is turned off. So if I'm giving C, then this one is turned off. Okay, now you can see deseparation. We can see clearly A and C will be deseparated by B, Why? Because if you turn off B, the connection between A and C will disappear. In other words, they are separated by B. This is deseparation. And also you can see, oh, A and C will be conditionally independent because there are no information flow from A to C or from C to A. And they do not share any common information, right? And similarly, you can see, probably that's enough. So deseparation is a property of the graph. And if A and C are separated by B, basically, that means if you hold B, or if you condition on B, there is no way for A and C to be connected, to be related, according to the mechanisms. Is that the answer to your question? In case it's not clear, please just give me some hints. Okay, faithfulness. Now, in this example, we have 3 variables, and not surprisingly, we have this causal graph. Health condition influences affects mortality risk, and okay, questions. Health. So deseparation is a separation between 2 connected components. If I understand correctly, yes. So deseparation is the relationship between involving 3 things. So it's the relationship between 2 variables giving another variable, or the relationship between 2 variable sets giving another variable sets. Okay. So here, this is the causal graph. We have, suppose it's linear with linear coefficients. Causal strength is A, B, C, right here. If by accident A equals minus BC, what will happen? Now you can see health condition will be independent from mortality risk, although the former is actually a cause of the latter, right? And you cannot see this independent relationship from the graph by applying Markov condition, right? They are not deseparated. Actually, they are not deseparated by anything. Why? Because we have an edge between them. If there's an edge between them, you can never deseparate them by giving anything. So this is the violation of faithfulness. And in this case, you can imagine why faithfulness is violated. You can imagine why those 2 variables, although causally connected, are actually independent. This is because we have other things. We also have selection process, right? We want to optimize a lot of things in this process. This is the only part of the causal graph. We want to enjoy a life, right? We want to enjoy our life. That's why finally health condition can be independent from mortality risk. So here, by assuming faithfulness, we just get rid of this possibility, meaning that if we have this causal graph right here, then health condition cannot be independent from mortality risk. Okay, and generally speaking, that's true. Why? Remember modularity. So the generating process for this variable specified by a particular structure equation model is not related to any other structure equation model. In other words, A and C here shouldn't be related to B at all. They are chosen independently by nature, right? And if that's the case, then the condition for this equality to hold true would have measure 0. That means, oh, if this is really causal graph, then the violation of faithfulness has measure 0. In other words, in most cases, we should trust faithfulness assumption. Of course, if you have finite data, it's possible that the faithfulness assumption is approximately violated, right? That's another issue. And there are some very nice papers trying to deal with faithfulness. So you can just search, you can just do a Google search if you want to see how to deal with the violation of faithfulness and how to detect the violation of faithfulness and so on. For now, we assume faithfulness. Okay. Now, given this, we can do causal discovery. And we are going to see 2 types of classical methods for causal discovery. The first one is called constraint-based method, condition independent-based method, and the second one is called score-based method. We start with the constraint-based method. Now, we have two questions to answer. We have data. From data, we discover independence and conditional independent relations, right? First, how can we find the skeleton of the causal graph? Is it possible? If yes, how? The answer is yes. Later, you will see why. And second, can we go further? Can we determine the causal directions? Yes, we can determine some of the causal relations. Here, you can see, basically, you can see how we can solve the problem. So we want to make use of independent and conditional independent constraints to find essential information of the causal structure. We now assume causal Markov condition, which is kind of widely assumed, and the Feynman's assumption, a typical assumption for causal discovery. And the typical method is called the PC algorithm. P is for Peter, C stands for Clark. So it's Peter Spertis and Clark Glimmer, basically the first letters of their first names. They are my senior colleagues. They came up with a lot of classical methods for causal discovery. Now, as the answer to the first question, remember, we want to find the skeleton or adjacency information of the graph. Then we have this theorem. It says that if two variables x, y are adjacent, two variables x, y are adjacent if and only if they are dependent, conditioning on every subset of the remaining variables. In other words, as long as x and y are conditionally independent given anything, then they are not adjacent, right? This is very nice. And you can prove this very easily. Why? Because if they are conditionally independent, then they are disseparated by something. If they are disseparated by something, then they are not adjacent, because any two variables that are adjacent cannot be disseparated by anything. Okay, this is the first part. By doing conditional independence tests, we can find the adjacency information. And then we want to find the directions. Remember the definition of this structure, right? Right here, you can see, if we have this ground truth, then we have independence between y and z given x. And then we cannot determine the causal structure. All those three possibilities will have the same conditional independent relationships, right? However, in this case, if we know we have three variables x, y, z, if we know that y is independent from z, then we know y and z must be causes of x. This is this structure. So if you discover this structure, you can determine causal direction. And then you can go further. You can do orientation propagation. Later you can see how we can do so. And in general situations, we may not be able to find a unique structure, and we have to represent the set of solutions by a pattern. And this set is known as the Markov equivalence class, because all members of this class will have the same conditional independence or independence relationships over the variables. Later you will see the definition. So let's have a very quick look at the procedure. So here we have data, x1 for x1, 2, 3, and 4. From data, we can discover independent conditional independent relationships in some way. So suppose we have an oracle procedure to infer independence and conditional independent relations between the variables from data. Now, since 1 and 3 are independent, we know they cannot be adjacent. Since 1 and 4 are independent given 2, we know they are not adjacent. The same thing happened to 3 and 4. And then we can go further. Right here, 1, 2, and 3 form a V structure because 1 and 3 are independent. We know causal structure, causal direction must go this way. And then we know the direction between 2 and 4 must go this way. Otherwise, if it goes this way, we are going to have a V structure, which is fake. We can determine whether it's a V structure. If this is a V structure, then x1 and x4 would be independent, but they are not. That's why it's not a V structure. If it's not a V structure, then this direction must go this way. Okay, so this is what we can do. Now you can see another example. I'll give this example step by step. So suppose we have data generated by this causal graph, you just saw, and then we begin with this fully connected graph or complete graph in which each pair of the variables is adjacent. There's edge between them. Then first we start with the unconditional independence tests. Now we can see, oh, we just consider each pair of the variables. We see 1 and 2 are independent. Then we can get rid of this edge. For all the remaining pairs, they are not independent, conditioning on nothing. So this step will stop, and then we go to next one, where we condition on a single variable to see whether variables are independent. And then we see when 1 and 4 are independent, given 3, we get rid of this edge. And furthermore, we see 2 and 4 are conditionally independent given 3, and we can get rid of this edge. And then, according to the PC procedure, we will stop, because for PC, every time we just need to condition on a subset of the adjacent variables. Now it's enough. We don't have to condition on 2 variables. So we'll stop here. This is the first step. We just found the skeleton of the causal graph. And then we find the V structure and then do orientation propagation. Right here, 1 and 2 are independent. Then we have this V structure, as you can see from this V structure, and then we do propagation. So propagation has 4 rules and they are complete, meaning that if you can orient this edge, then by making use of one of the 4 rules, you can do so. So here you can see 2 examples. The first one is to avoid fake or spurious V structures. I know this direction. I don't know this direction right now, but I know this is not a V structure. Why? Because all V structures were already discovered at the beginning of step 2. Then I have to orient this guy this way, because otherwise I'm going to have a fake V structure. And this is away from cycles. Right here, I know this direction, and then for this one, I have to go this way, because otherwise I'm going to have a cycle violating the assumption of DAG, directed acyclic graph. Later, you can see how we can deal with cyclic graphs with loops. But right now, we assume the graph is acyclic. Okay, now you can see the solution. Now, how you can see in this example, we have direction for all edges. But in many cases, we don't have direction for all edges. We have to represent the solutions. So first of all, we say 2 DAGs, directed acyclic graphs, are independence equivalent or Markov equivalent if and only if they have the same skeleton and the same V structures. Okay, and then we can use the patterns or CP-DAG, completed partially directed graphs, to directed acyclic graphs, to represent the equivalence classes, a set of equivalent DAGs. So essentially here you can see how we can do so. In total, there are only 3 possibilities for the edges. Right here, they are not adjacent. Right here, they are adjacent, but we don't know the direction. It means that, oh, in some members, the direction goes this way, and in some other members, the direction goes this way. We cannot determine it in the solution. That's why we don't have the direction. And right here, it says that, oh, I know the direction. Direction must go from 1 to 2. Then we can just use a directed edge. So, okay. And this is a pattern to represent the Markov equivalence class. So in this Markov equivalence class represented by this pattern, in total, how many DAGs do we have? How many possible solutions, how many possible DAGs are contained by this pattern? Maybe you can give an answer right now in the chat window. So I wait 5 seconds. How many members, how many DAGs can be represented by this pattern? Okay, no one. So into the clear, right here is 2, right? It's just 2. It can go this way or that way. Okay. Now come the second example. Suppose we have data, enough data, right? With a rather large sample size. So generated by this graph, then we can do the same thing. We start with this complete graph. Right here is just the edge between A and E. It's ugly, but it's just a direct, just an edge. So we start with the unconditional independence test. Right here, no pair of the variables is independent, conditioning on nothing. And then we condition on one variable, and then two variables, and so on. So finally, we can stop here, and this is the skeleton. It's correct. And then we can find a V structure right here, CDE formal V structure. Why? This is because C and D are conditionally independent given B, which does not contain this variable. That's why we know, oh, right here, C and D must point to E. Otherwise, if one of them goes in a different direction, then in order to make C and D conditionally independent, E has to be part of the conditioning set, right? In order to make them de-separated, we have to condition on this guy. Otherwise, this path is always open. If you do not condition on E, suppose the direction goes this way. But if the direction goes this way, we cannot condition on E. If you condition on E, they will become conditionally dependent. Okay, so now we have this graph, this pattern. Do you think we can determine the direction between A and B, or between B and C, or between B and D? Yes or no? In this case, no, we cannot go further. We cannot determine directions. And then a quick question. This is the pattern. How many graphs, directed acyclic graphs, can be represented by this pattern? We know right here direction can go this way or this way. And right here can go this way or that way, and so on. So in total, how many graphs, directed acyclic graphs, can be represented by this pattern? Good, good. So I'm not going to give you a solution, but I want to give a wrong answer. Some people may say 8. Why? Because here I have 2 possibilities, here I have 2 possibilities, and so on. So the total number of possibilities would be 2 times 2 times 2, which is 8. It's wrong. Why? Because we cannot have a fake V structure. We cannot allow 2 of them, this one and that one, to go to B at the same time, because if that's the case, we are going to have V structures, right? So we can just consider all possibilities that will not introduce any fake V structure right here. Then you can do a calculation. You can immediately find the solution regarding the number of possible DAGs in this pattern. Now let's have a quick look at some real applications of this search procedure. Sometimes we say causal search because you want to search for the causal structure. Right here we have data for sex, IQ, CP, college plans, PE, parental encouragement, SES, socioeconomic status of the family. And the data were collected basically from more than 10,000 high school seniors. And this is the graph given by the domain experts right here. Actually, they apply the method, my colleagues apply the method, and they recovered almost everything in this ground truth provided by domain experts. Almost everything with a single difference. From this graph, can you guess what the difference is? For instance, can we recover the direction between SES and IQ? No, this is the only difference. Right here, with the solution given by PC, will give an undirected edge between SES and IQ because we cannot determine the direction right here. All the remaining edges are directed because we can determine the directions. For instance, here, for this one and that one, this is a V structure. SES, sex, and PE, the V structure. and so on. So now you can see we can really recover information about the causal relations by analyzing observational data. And in this case, if you use PC, sometimes we cannot recover the complete information, but we can trust the information if you have enough data. This is the second example, which you just saw at the beginning. So you can apply PC combined with our kernel-based conditional independent test, because here we cannot really assume the relationships are linear. They can be very complex. So you use the non-empirical method for conditional independent test. Right here, you can see the result by PC combined with this test method. Some of them, some edges are directed, some are not. So right here, you can see if you have some background information, for instance, we know location. This is location, this is climate. The direction should go from location to climate, not the other way around. If you introduce such information, then you can do orientation propagation. This guy must go this way, otherwise I have a fake with structure. Hey, immediately we have a DAG. Now we have a complete DAG, direct acyclic graph. A lot of information right here has been discussed in the literature. For instance, here, climate and cranial size. So basically, if it's very cold, like in Russia, right? People tend to have a larger cranial size because it's better to warm the air before you really inhale the air, right? So the cranial size would be larger. From the selection perspective, you can explain why we have this causal influence. However, we can still discover something novel compared to the information that discussed in the literature. Right here, in the literature, they say the diet is a cause of cranial shape differentiation, which means what you eat will change how you look. It's fine, right? However, here, yes, we agree, but at the same time, we can see that relative to this set of variables, diet is not a direct cause of cranial shape differentiation. When we have an age, we just mean that, oh, this guy is the direct cause of that guy. So right here, by analyzing data, we have not only causal information, but also very detailed information regarding whether this variable is a direct or indirect cause of some other variable. And this is detailed because we know that diet influences cranial shape differentiation via another two variables, including level of attrition in teeth and some behavior. So now data analysis is really cool because I can really discover very detailed information regarding the variables. If you just make use of domain knowledge, it's really hard. Okay, good. Now let's have a look at some particular examples. So far, we have assumed that there are no confounder in the system. In other words, we assume causal sufficiency. There are no unmeasured direct cause of two variables in the system. Okay, now let's look at the examples. We want to answer the following question. Is it possible to say anything about the confounders? Example 1. We see independence between 1 and 2, independence between 1 and 4 given 3, and independence between 2 and 4 given 3. Okay, this is the graph. Previously, we already have this. Now the question is, do you think it's possible to have confounders behind 3 and 4? Yes or no? Is it possible to have this confounder? C? The answer is no. Why? Because if you have this confounder, then x1 and x4 will not be deseparated by 3 because of this path. If you condition I3, this path will be open. In other words, x1 and x4 will not be independent given x3 if you have this confounder. But now we know 1 and 4 are independent given 3. Then we know there are no confounder. And furthermore, we know in this case, no matter what, right? We know x3 is a direct cause of x4 without the confounder. This is super cool because by analyzing only very few variables, we can really say whether it's possible to have a confounder. We can say something very universal, right? That's cool. We can exclude the possibility of having confounders. Okay, this is the first example. Second example. You can just have this is example. So let x1 be rainy, and this is wet ground, slippery. Now you can see, oh, as long as I know that x3 is not the cause of x1, and then given the independence between x1 and x4 given 3, I know that x3 must be a direct cause of x4 without the confounder. Okay, example 2. 1, 3 independent, 1, 4 independent, 2 and 3 are independent. From this, you can immediately write down something, right? You know, oh, 1, 4, 1 and 2 are adjacent, 1, 4 not adjacent, 1, 3 not adjacent. 3 and 1 not adjacent, 3 and 2 are not adjacent. So basically we have this. For now, just ignore L, right? And now, do you think they're the confounder between x2 and x4? The answer is yes, there must be confounders behind x2 and x4. First of all, if there are no confounder, then you can see 2 and 4 must be adjacent. And if the direction goes this way, from 2 to 4, to save time now, yeah, let's spend some time here. If this guy goes this way, now you can see, oh, x1 and x4 will not be independent because we have a directed path from x1 to x4, right? So this guy cannot go this way. And similarly, this guy cannot go this way. And how can we explain the phenomenon? We have to introduce a confounder. Actually, there's a confounder behind the x2 and x4. This is the only possibility. Okay. So here, in this case, we know although x2 and x4 are dependent, and they are conditionally dependent given anything, still we can infer that there must be confounders behind x2 and x4, and furthermore, that there is no direct causal relationship between between x2 and x4. They are not directly causally related. They are dependent because of the confounder. Okay, you can think of examples. So let x1 be whether I'm sick, 2, whether I'm in this lecture room. Suppose we are in the room. x4 is whether you are in the room, and x3 is whether you are sick. Whether you are sick. So now you can see, you can verify those conditions. 1 and 3 are independent, 1 and 4 are independent, 2 and 3 are independent. Of course, we can make this more general. We can just condition a lot of variables, doesn't matter. Now, given this, I can just infer that x2 and x4, although dependent, are not causally related. They are confounded. So I'm in this lecture room, you are in this lecture room, right? Because of something hidden, because we have lecture here. So even in our daily life and in history, in social sciences, we can make use of such rules to discover causal information by making use of the observed information. Okay, so just now you just saw something about whether we can determine confounders. More generally, the problem that follows.
We have about 2 minutes left, so maybe we can do a small recap before starting a new topic.
Yeah. Since we started a little bit late, so could you give me 3 minutes?
Of course.
Yeah.
All right.
Okay. So then, because I have to finish this part, otherwise, yeah, probably we have to go from the beginning next time.
Yes.
So, yeah, to make it to formalize the problem, now we have this issue to address. We have a direct cyclic graph over a lot of variables, right? Like you can see from here, we have a direct cyclic graph over x1, 2, 3, 4, and L. But unfortunately, we only observe some of them. x1, 2, 3, 4. This guy is not observable. Then we want to analyze the information between the observed variables, right? So in this case, as you can see from this example, the observed variables may not follow a DAG or directed cyclic graph. If you use a DAG, you have no idea, you have no way to represent the dependence or relationship between x2 and x4, right? So here, what can we do? We have to use another thing called a PAG, partial ancestral graph, to represent the relationships between the observed variables to represent the relationships between the observed variables. Given that the causal relationships happen to a larger set of variables, including this observed set of variables, right? We have additional variables omitted in the system. So here, all those methods or those examples have been considered in the FCI method. FCI is the fast causal inference published in the 1990s. So right here, we cannot use a pattern to represent the output of FCI. We have to use, in other words, we cannot use CPDAG, completed partial and directed acyclic graph. We have to use PEG. So for PEG, in total, we have 5 situations. We have 5 possible edges. Not adjacent. X2 is not an ancestor of X1. No set deseparates X1, X2. Right here, X1 is the cause of X2, and there must be a confounder. So in total, we have those 5 possible situations regarding the edges. Okay, so I'm going to stop here, and let me just give a very quick summary. Next time we'll start from here. So yeah, okay. So first of all, the key message is that the conditional independent relations can be used to discover information of the causal structure. And to do so, we have to make assumptions. One is the causal Markov condition, the other is the causal faithfulness. You know what's there, and you know in what situations faithfulness assumption is violated, and you know why in a general situation this condition should hold true. And then we can develop the constraint-based method. Here by constraint, I mean conditional independent constraint. And we can also discuss, we can also consider or deal with the confounders under some assumptions, as you can see from the FCI method. And next time you will see how we can use score to do causal search very quickly. And also you will see some practical issues, including how to deal with missing data and how to deal with non-stationary data. Okay, thank you. If you have questions, maybe you can stay. Otherwise, see you tomorrow. Thank you.
Thank you very much.
Sorry, I'm running a bit late.
No, it's fine. We'll start a bit late, and we can now wrap up very nicely and continue tomorrow. Otherwise, we'll have now a break for the participants, and then we'll have our next session at 11 a.m. And we'll continue with you tomorrow.
Yeah, great. Have a nice day. See you tomorrow. If you have questions, just, yeah.
And all questions that appear, we are collecting them in Slido. So tomorrow we'll be asking them. So if there is someone who wants to ask something but couldn't do today, tomorrow will be the occasion.
Wonderful. Okay. Thank you, Rodrigo, and thank you, everyone.
See you tomorrow, Kun. Have a nice day.